Okay, so so before we move on to the concept of, say, entropy, let me just mention the idea of a refrigerator and um, a heat pump. So a refrigerator is essentially a heat engine running in reverse. Okay, so it's, it doesn't have to be a Carnot engine. Okay, and of course Carnot engines are idealized engines, whereas real life refrigerators are not Carnot engines. All it does have to be is that it has to be a heat engine that is running in reverse. What does that mean? That means that we have some cold, some object or some reservoir Tc, and Th is a higher temperature, and we do some work on this machine, and typically this is work done with the help of a source of an electrical source, right? And this is the refrigerator, and what it does is that it then draws some heat, and then it dumps, some heat into the hotter reservoir, right? So this is a refrigerator. Now, for the refrigerator, we don't really care about measuring, how much heat it's dumping into the atmosphere. That's a part of the backside of the refrigerator. You see that the backside of the refrigerator in your house is hot, is warm. That's where it's dumping the heat that is absorbing. And the cold reservoir is your vegetables, right? Or your food. If you're a carnivore, it's the chicken. So now for the refrigerator, we want to define the efficiency in a different way. So the efficiency that we want to define for the refrigerator is, how efficiently can it take this work W and cool down, and for a given amount of work, how much heat can it like take out of the cold stuff, right? So that's basically, if it's if it can be done very efficiently, then of course it's a very good refrigerator. So I don't know if real life refrigerators have a rating, efficiency rating, but I'm a theoretical physicist, so this is basically how we define the efficiency of a refrigerator. Okay. Now, so suppose that we have a refrigerator which is a Carnot engine. So suppose our refrigerator was a reverse Carnot engine. Okay. In that case, the work will be given by QH minus QC. Here, all these things are positive, right? And then for the Carnot refrigerator, the efficiency you can show is QC divided by QH minus QC. Now, if our Carnot engine is like an ideal gas, then for ideal gas, QC over QH is TC over TH. Okay, and then you can the Carnot engine refrigerator is TC divided by TH minus TC, and this can be efficient more than 100%. Okay, and there is no like violation with any law. And this is because we are not really taking into account how much heat it's dumping into the environment. So a heat engine, on the other hand, is exactly this object, but in the heat engine, we are also interested in QH. So not a heat engine, a heat pump. So what is a heat pump? A heat pump is essentially a heater, or it's actually not a heater. It's a saying. It takes heat from a colder reservoir and then it dumps heat into a hotter reservoir. So this could be your home, for example, right? And for the heat pump, the yeah, I don't think I have. I wrote down the notes about what the efficiency of this is. So the heat pump is essentially the same thing, but there we are also interested in, we are interested in how much of the heat is actually being, dumped into the hot object. I think the heat something the efficiency. What do you think would the efficiency be? Right, it'll be probably something like QH over W, right? Yeah, I think I maybe let me check. I forgot what the heat pump is.
Sir, is QC by QH is equal to TC by
Yeah,
TH? Is it
yeah,
for
yeah.
only the ideal engines?
Um, yes, yes. Um, just hang on 1 second. I think the cat wants to go out. Our meetings. Okay. All right. So, any other questions?
Sir, if it wasn't an ideal engine, what did we have to consider in the QC by QH is equal to TC by TH equation?
Um, Even how would that be changed?
You said this is only for the ideal engine.
It is for the yes, it is for the ideal engine. If it weren't so, then I'm not sure how that would be changed. I would have to think about it. Okay, if there's friction involved, then it'll change, but I'm not sure exactly how.
Okay, sir.
Hmm. Okay, anything else?
No, sir.
Okay, all right. So